started.
Okay, wonderful. Well, welcome. I am Keely Seabine,
Matthew Veterick.
and we are with Seabine Acoustic. We're going to be talking today about acoustic design strategies for education facilities. We are Seabine Acoustic, and these are some of the services that we provide for architectural and environmental acoustics. This is an AIA-approved CEU. And you'll receive credit for this if you were an AIA member. This material is copyrighted, and
We're going to go ahead, now that we're getting into the presentation, shut off this camera so you guys can focus a little bit more.
okay. So today we're going to get started, and we are going to look first and foremost at some of the research that has gone into classroom acoustics over the last 20, 30 years or so. We're going to learn about some acoustic finish design so that we can optimize the acoustic learning environment. We're also going to go over some concept HVAC design strategies for schools to help optimize the HVAC sounds and understand appropriate sound transmission design for typical classroom spaces. When we think about classrooms and schools are really comprised of learning communities. When we look at the word community, its etymological derivation is communis from Latin, meaning a fellowship or relation or feelings. It can also mean life in association with others, or an area with people of a common character or identity. And when we think about classrooms, we're looking at helping our communities be able to communicate. When we look at communicate, it comes from the Latin communicat, which means to make common, to share, to give something intangible to another. And so to enable effective communication in learning environments or learning communities, this is really at the heart of what classroom acoustics is looking at doing. There's been a lot of multidisciplinary research that's been going on since the 1990s, even before, that looks at classrooms. It looks at the ages of the listeners, what their hearing abilities are, and acoustic metrics, and tries to make sense of what is actually happening in the classrooms and how best to help students learn and how teachers teach. So one of the important concepts in classroom acoustics is looking at background noise. This is essentially how much sound is present in the room as a baseline from HVAC sounds, from exterior sounds, and whatnot. And then also looking at how loud the speech sound level is. And so if we have a relatively low background noise level, and we have a speech sound that's 15 dB or so higher than your background sound, that's helpful in classroom acoustics to facilitate learning. However, when we have background noise that's too high, whether it's from HVAC noise, whether it's from a noisy site with airplanes passing overhead or trains passing, sometimes this ratio between your sound source signal and your background noise signal shrinks, and you get a lower signal to noise ratio. When that happens, it has been found to be more difficult for students to be able to hear and comprehend. Back in the early 2000s, Bradley and Sato did a study on this, where if you see the x-axis here, you see the signal to noise ratio kind of goes from negative, meaning that the noise is actually louder than the signal, to 0, and to positive, We see this trend where when we have negative numbers for the signal to noise ratio, meaning that the signal is barely above or not even above the background noise, the intelligibility is really all over the place. It's very low. It's the spread is just all over the place. When we start getting up to about a 15 dB signal to noise ratio, that's when we start seeing the intelligibility get up to, around 90% or so. And so this is kind of a important dividing line, and part of the background of where this idea of trying to maintain a 15 dB signal to noise ratio really comes from. Part of the reason why background noise should really be limited in classroom acoustics. And this is another study, sort of similar study, where it looked at typical hearing populations and then also moderate to severe hearing populations. And we again see this trend. The y-axis is a little different here. This is speech perception score, and signal to noise ratio here. But we also see this trend of, when we get to about 15 dB speech to noise ratio, you're getting much higher speech perception scores, which is much better in terms of understanding. In any given day, 40 to 50% of the 50 million students hear as though they have a hearing loss. And this could be because the English is a second language for them. It could be because they have a middle ear infection. It could be that they have any sort of special needs. And so this is just very important to understand that we have a significant population that does not necessarily hear like they have typical hearing. And so it's very important to understand that when we're designing our classroom spaces. Again, a similar study as well, looking at this idea of signal to noise ratio and a fraction better than 95%, and looking at different grade levels. And seeing that, once we get about above 15 dB signal to noise ratio, we start to see these upward trends of better comprehension, better intelligibility scores. So this is just a very important concept and kind of the background for why classroom acoustics and dealing with the acoustics in these spaces is so important. When we look at the different components of speech communication in a classroom, our source is typically our teacher. Our receivers are our students, and the direct path of sound from the source to the receiver is shown here in the solid line. But sound propagates in many directions, hits many surfaces all throughout the room, and it reflects back to students. There's also AC noise, there's exterior noise from outside the classroom, there's exterior noise from adjacent spaces. So there's many, many different noise sources that are kind of competing in this one area where learning is supposed to be taking place. We also, now this was a study done in 2009 by Bradley and Yang that looks at reverberation time, T60 in seconds, and looks at speech perception scores. And what we're seeing here is that very distinctly, age makes a big difference in the perception of speech as you are going up the grade level. So grade 1, we've got this curve here where 70% or so of speech perception is occurring over the ranges of reverberation time. That hops up about 5% when they get into grade 3, another 7 or 8% in grade 6, and by the time you're adults, your speech perception on average is ranging much higher, 90% or so. So it's very important to understand that younger listeners have different needs when it comes to speech perception. And we also see here that we have this kind of little hump in these graphs, which is basically showing that we have this sort of ideal reverberation time in here where the 0.6 to 0.7 or so second reverb time in a classroom is actually resulting in a slightly higher speech perception scores for all of these populations, which is kind of makes sense for why some of the acoustic criteria is what it is today. We'll get into that a little bit later.
So that was a little bit about some of the research behind this, but now we're going to go ahead and look at how this affects the architecture even more specifically as some architects may be looking at this. And we're going to deconstruct an actual impulse response from a room to kind of look at all of these different items. So an impulse response is a tool that can be used to help allow analysis of the architectural design features of the room and kind of look at how they the different features contribute to what people hear. And this includes the shape of the room, the actual volume, the materials that make up all of these surfaces, and just the background noise levels itself. And as Bernard Lettner had said, designing with it being sound, designing with precision, it becomes a building material. So sound can actually be a building material. So the first thing that we're going to start out with, and again, we're kind of building up our impulse responses. We have our background noise. So this is kind of constantly going to be in there. And so this background noise might be made up of the AC noise, site noise from things that are happening outside, whether that's the mechanical plant, whether that's the road nearby, or if you've got trains or airports nearby and you have things like that impacting the site. The students outside the classroom, so maybe they're in the hallway or in the classroom next door and they're still being heard, as well as then the students inside the classroom themselves are, again, creating noise. So this is all going to create our background noise. Then that direct sound, that sound from the teacher to the student, really, as we're trying to look at this. So we want to maximize that direct sound. And so that's going to be made up of elements like the teacher's voice. So the strength of their voice, the direction. Are they facing the whiteboard when they're talking, trying to teach something, or are they actually facing the students? The teacher's diction as well. And in a large space, there may need to be electronic amplification of the teacher's voice. The other thing is, again, that distance between that teacher and the students, that's going to have an impact on this sound level as well. And that's where, again, in those large spaces, you do add things like the electronic amplification. Then we're going to want to go ahead and maximize our early sound reflections. So these are going to be reflections off of kind of hard sound reflecting materials on the ceiling. In some of these cases, we want to strategically locate these. So we don't want them everywhere, but we want to focus on where they need to be. And they're primarily going to be near the teacher or near the student, because in some cases we also have the students talking and talking back to go ahead and respond. So we also have these not just on the ceiling, but on the walls nearby. But again, you want to strategically look at this. This isn't going to be everywhere that you're putting reflecting surfaces, but it's kind of has to be strategically done to make sure that you have this. And we're going to kind of go over some of these a little bit more when we talk about finishes in a minute. And then the one thing we do want to look at is also to control and minimize that reverberant tail. So that RT that we were looking at, we don't want it to be really long. So we want to kind of control that. We don't want to get rid of it completely because then sounds and speech is heard a bit differently. But we want it to be appropriate for the room volume itself. And again, this is strategically located sound absorbing material instead of sound reflecting material. So you do want a mix of both typically.
So these are just a couple of slides of some concepts for acoustic finishes for acoustics in a classroom. For typical lecture mode, we may do something like NRC 0.7 acoustic ceiling tile on the ceilings. and have some 1-inch thick acoustic wall panels on the upper side walls in the room. If we want an enhanced lecture mode, if this is like Matthew was saying, perhaps a larger lecture hall with many, many seats, we may want to add in this orange color here, gypsum board reflecting cloud. Now, it doesn't have to be gypsum board. It can be any reflective material, and it doesn't have to be this angled shape. It could be curved. It could be another shape, but essentially what that is doing is it's helping to enhance the presence of the first order reflections in the room. And that can be very beneficial, especially in larger room volumes. We've got the same kind of base components of ACT with an NRC of 0.7 and also some 1-inch thick acoustic wall panels for this. So looking at this another way, some ideas here are trying to limit the room volume. So you're not having huge ceiling heights and huge room volumes. The area of absorption should ideally be more than or equal to the area of the floor. Acoustic ceiling tiles on the ceiling and acoustic wall panels on the upper side walls, and having this for like a large lecture hall where we have this orange kind of sound reflecting surface kind of more towards the front where the teacher would be positioned if they have a fixed teacher location, and the other treatment that I've previously mentioned. And now some enhanced finish design for acoustics. If we're looking at kind of group learning areas, then where we're going to have students kind of sharing, talking all at once, we may want to increase the NRC of the acoustic ceiling tile to 0.9. This will help absorb more of that sound energy in these spaces where there's going to be much more sounds going on, because for most of the time, the students will all be talking and interacting with each other. And again, 1-inch thick wall panels along the upper side walls. If we want to enhance this even further, then adding in another layer of 1-inch thick acoustic wall panels could be considered as well, going on the kind of lower sidewall areas as well. So these are just kind of some acoustic finish concepts to consider for kind of group learning situations. With that, we're going to dive into HVAC design for acoustics.
Yeah. So as we were saying before, is the background sound level can play a key role in the students understanding what's actually being presented. So HVAC systems can be very critical in helping maintain that signal to noise ratio that we were talking about earlier, where you want it to be at least 15 dB or higher for that signal to noise ratio. And again, with those younger students, you need even more, closer to 20 decibels above the noise is what you'd be looking for. But the background sound level of a classroom, so that you don't have to have additional vocal effort and strain on the teachers, is gonna probably want to be around NC 30 to 35 dBA. And we're going to see some of that again in some criteria a little bit later as well. So that if that's that background sound level, that 15 or 20 decibels above that for the source is much more easily achievable without additional effort. But in the HVAC system, some of the things we're going to want to look at is, we have our mechanical room here. We want to separate that from our classrooms. We don't usually want to share that wall. We want to have some sort of buffer space because we have a lot of noise going on in this mechanical room. We're going to go ahead and want our kind of longer supply and return ducts so that we can go ahead and have that air a little bit slower by the time it gets there, as well as then it reduces sound as it travels through the ducts through more distance. Again, these are ducted systems. We're not looking to put just kind of a grill on the wall and have the AC closet there with a fan coil unit directly in the closet. No return duct. That's going to, again, be more noise if you have that in that case. And again, these we're looking at kind of moderate duct velocities for the air velocities in here because you don't, you may not need to be very low air velocities like you would in a recording studio, but they can still make more noise and it impacts kind of noise into that by faster moving air. Vibration isolation equipment's also critical for the equipment. So spring mounts and spring hangers for the equipment is going to be very useful so that you don't go ahead and have structure-borne noise being added into this as well. So we're going to go ahead and look at, a fan coil unit for, let's say, a classroom here. We don't want to go ahead and put this right up above an ACT ceiling or right on the wall. It's going to be a lot noisier that way. And some fan coil units, some of them can get pretty loud too. So what we want to do is we want to put this in a closet itself. And then we're going to go ahead and make sure we have those ducted supply and return runs. Now within those ducts, if this is a really loud unit and we're just a generally loud unit, doesn't even have to be really loud to see this, we're going to probably look at adding silencers. So duct silencers will help us to control the sound level that's coming out of these that we're going to want to look at as well. And then on this, as we were saying, vibration isolation is important. So in here, we're looking at spring isolators on this unit to, again, help stop that. So all of these things kind of go into account. Some of them may be able to be, the silencers may be a little shorter or longer, depending upon how noisy the equipment itself is. So now if we actually look at this more in a plan view with the classroom around it, we've got our closet here and we've got our supply and return ducts. Again, we have these separated for this. We also are looking for some fairly decent duct lengths, as you can see here. It's not just poking right out of the wall in here. And we don't just have that grill on the wall and an open return into that closet as its own plenum. You can also see there's a lot of length to the flex duct. So acoustical flexible duct is typically recommended in about 6 to 8 feet before the diffuser. So again, this helps that kind of last little spot that you can have some absorption. Most duct work otherwise isn't lined, while it still does reduce sound and can be lined in some cases too. It's acoustical flexible duct is more commonly seen, and again, right there just before the diffusers helps to reduce that sound level a bit more. So now if we look at, say, a mechanical penthouse up on the roof, or if we've got this is just an upper floor mechanical room above some classroom spaces or other occupied spaces, we're going to look at some of the same things, but a little bit different. Again, we're looking at this as a fully ducted system. We've got here the silencers within this as well. Depending upon the space this is over, we may have something like a floated slab here or a floated floor to help produce airborne sound. We do have to still have vibration isolation for the equipment. We have to be careful and look at what that specific is, how that interacts with that floated slab does need to be taken into account. So there's all sorts of things that do need to be looked at. You don't just poke the hole right through the bottom of the unit right down below. This might be on a multi-story school or just up on a roof in a penthouse space. And again, so looking at this in plan, we have here we're going to want to bring those ducts out down over a corridor or maybe something that's more, a storage space, somewhere that's not as critical. And then we're going to run them through the hallway a bit to get that longer length that we were talking about. We also want to keep our VAVs outside of the classrooms and over the corridors if we can. You may need a silencer after the VAV because they can still add more sound right there. And so now you had a lot of duct length to take care of the sound from the main unit, but now you do need to reduce some from those VAVs. Some manufacturers have them that are integrated into the, and so those are options. But again, we still have otherwise fully ducted return. We've got flex duct here. all of this. It's pretty balanced layout as well for the supply side that we're looking at. So we're trying to see after this to get down to those, again, NC 30, kind of 35 dBA sound levels that we're looking at. So another thing on a rooftop, maybe not in a penthouse, but you might have a big package unit up on the roof. Well, again, you want to make sure that you still have spring isolators on this. And this might be a rooftop spring curb, or this may be springs on top of dunnage that's lifting this up. Again, we've still got silencers in this ductwork. We're still ducting both of these systems completely. We're kind of looking at all of that. So you want to focus on things of that nature too. Again, it's a lot of the same concepts that we're going over. Again, you can see here, again, you're coming down over kind of a storage or a restroom space. Again, these ancillary spaces, and have some buffer space, if you will. And then so you don't just have that right here at the wall, you run out a bit further, you've got flex duct here. So again, a lot of similar concepts, but they're dealt with a little bit different depending upon which one of these we're looking at.
Now we're going to jump from HVAC to just some of the site noise and siting and space planning. If we are lucky enough to be working on a new school, then we have some flexibility with where we might be able to locate some of the buildings. If we have noise sources like highways or trains, those kinds of stationary noise sources, we might want to look at, well, what could we do in terms of orienting the buildings to kind of buffer some of the main classroom spaces, buffer maybe some of the performance spaces, so that there's buildings that act as noise barriers. These buildings here can kind of act as a noise barrier if we've got a highway coming along the north side of the site, and all of the classrooms and performance spaces can be shielded. So just something to kind of think about. Also, you want to think about where are you putting the central plant or HVAC units? Are they going to be near sensitive spaces? Or should they maybe be near a more noisy space like a gym? So just some concepts to really think about as we are thinking about how the exterior site might impact our schools. We want to make sure, so when we're looking at the facade, we have something called an OITC, which is an outside to inside transmission class. This is basically a rating kind of similar to an STC that takes into account kind of the lower frequencies for transportation noise. And it kind of tells you how your assembly, how your wall or your window or your door or your roof may perform on site. And this is something that kind of goes along with doing a noise study on the site, a noise survey, where we're measuring and documenting sound levels to really figure out, what are the sounds that are anticipated on the site? What levels are they? How frequent are they? Are they something that's going to impact the site, or is it a fairly lowly impacted rural site? So just some things to think about. When we look at the STC, that's more for the interior partitions, we're wanting to try to make sure that we're selecting our walls, doors, and windows intelligently so that we're reducing sounds as much as possible between space to space, between classroom to classroom and teacher planning to classroom, restrooms and classrooms. Mechanical spaces are a big one. So we want to just make sure that all of these systems are being looked at carefully. One way to look at this is looking at oralizations. So when you have an STC rating of a particular number, let's say STC 50, it may be hard to understand, well, how much sound does that actually reduce from one space to the other? So oralizations are kind of tool that can be used to help people understand that. So this, oh, I get rid of that. We wanted to play a little oralization for you. So this is music. So we're standing in a classroom. And playing this through an STC 50 wall assembly. I'm not sure if you're able to hear this on your end or not, but you can still hear sounds being played through this. This is the approximate assembly that you can see listed here. We're still getting some of those sounds coming through, but at a much reduced level. So this is just a kind of tool that acoustic consultants can use to help clients understand tangibly what might be expected. And now this is if you bump up that sound level to 97 to 100 dB, you've got that same STC 50 wall. This would be in a band room, some sounds can typically be 97 to 100 dB. And so you can hear clearly that if this were a band room and they were playing that song, you would hear a lot of that sound coming right through an STC 50 wall, which is why STC 50 walls are typically not recommended for band spaces. So now we're going to jump into the Florida Building Code and talk a little bit about some new criteria for enhanced classroom acoustics. Matt's going to.
Yeah, so in the most recent edition of the Florida Building Code 2023, they've added this section, section 1211, to discuss enhanced classroom acoustics. And so what it really does is it just has a small line that says enhanced classroom acoustics are going to be required and shall comply with section 808 of ICC A117.1. And so this is where this is required is for any group E occupancy. So this is going to be your kind of K through 12 public schools and the enhanced class. So it's only going to be for volumes of 20,000 cubic feet or less for a classroom is what this focuses on. And so we have that, and section 808 basically says this is for classrooms not exceeding 20,000 cubic feet. But as we start to go ahead and go into the specifics, there's a few different items here. One is going to be the reverberation time. And so we talked about how reverberation time plays a role in how students kind of can learn and perceive earlier. So they've given you two ways that you can go ahead and look at this. There's a performance method where you can actually go and measure the reverberation time of the space itself. And if you're 10,000 cubic feet or less, then the criteria is that it's going to be 0.6 seconds, which, as we remember seeing from our curve earlier, is kind of right there at that kind of peak where we want it there. And then if you're between 10,000 cubic feet and 20,000 cubic feet, they allow that to be 0.7 seconds or less is what they're aiming for. And this is for fully furnished, unoccupied classrooms is how this is measured. Now, the prescriptive method does not allow the furnishings to be included, but it does allow you to looks at all of your kind of floor, wall, and ceiling surface finishes themselves. So this is actually using a calculation based on the NRC and surface area of each material of the floor, the ceiling, and the walls. So if you have wall panels versus gypsum board versus tile versus carpet versus ACT, all of those things can have an effect, and you can look at this a little bit a different way. The equation, again, is just kind of a volume divided by either 12 for the smaller size classrooms, the 10,000 cubic foot or less, or that the volume of the room divided by 14 for those from 10,000 to 20,000 cubic feet. We're actually going to do a really fast overview of this for an example classroom. And so say we've got our 28-foot by 32-foot classroom, 10-foot ceilings, pretty standard, with some tile floor, gypsum board walls, and ACT ceiling. So the ACT we've got here is an NRC of 0.55, a fairly basic ACT. And our gyp walls and our tile floors have an NRC about 0.05. So first we go ahead and we find our volume of the space, and we see that we're less than the 10,000 cubic feet. So then we divide that volume by 12, and we get this number 747 roughly here that we're seeing. So we're going to take that and we're going to go ahead and calculate out all of kind of the sub values for the floor, ceiling, and wall that we have here based on the surface area times those NRCs, and add those up, and we get a little under 600 here, which is again less than what we're required to have as our minimum. So when we go ahead and look at this, we have to kind of think, what can we do to get this up to meeting that building code criteria? Well, if we just change one thing here, we're going to change that ACT to an NRC 0.75 in this example. And that brings us up to about 777. So we're above that criteria level that we were looking at. So we meet that now just by changing out that ACT. And it can be just that fast to do one of these simple calcs for, again, this is a very simple room. You may have a lot more kind of materials and surface finishes than just one per kind of floor, top, ceiling, and wall. You may have wall panels that have to be added, and you may have areas of gypsum board and ceiling mixed in. So, bit of that.
So where the classroom acoustics, enhanced classroom acoustics requirements get a bit nuanced is in this next section here, where we have this 808.3 ambient sound level requirement. So within this requirement, it says that the greatest 1 hour average sound level shall be evaluated at the loudest usable location. This essentially means that we have to go, someone like an acoustic consultant would need to go and measure the sound levels on the site so that we can determine what the greatest 1 hour sound level is. And then it breaks it down even further into these other two categories that say sound sources outside of the classroom. So this is from sound sources, whether it's from the exterior or from the interior spaces. So that means that whether we have sound levels outside, like airplane overflights, highway noise, mechanical noise even, all of those sound levels need to not exceed 35 dBA and 55 dBc. And then we also have this other criteria for sound sources inside the classroom. This is basically sound sources from your HVAC, mechanical, MEP noise. Those should also not exceed 35 dBA and 55 dBc. And so kind of contained within this ambient sound level section is really a multitude of different kind of implied analysis that needs to take place. So we've got to measure the sound levels on the site so that we can figure out what the greatest 1 hour average sound level is. We have to take into account that sound level when we're designing the facade to make sure that those sounds from outside are not above 35 dBA, 55 dBc. Then we've got to look at all of our adjacencies, whether we've got a band room to a choral room, or a gym to a classroom. Those adjacencies, the sound levels going back and forth between those spaces cannot exceed 35 dBA and 55 dBc. And then we also have the noise from the mechanical system. So all of those together have to be looked at very carefully. And so this is actually a very kind of, it encompasses a large amount of scope for acoustic consultants to take care of this, especially in every single classroom. And just to note, this is the existing building code has a note in here that says in Group E occupancies where the work area is a level 3 alterations, enhanced classroom acoustics should be provided in all classrooms. And it has a note here about complying with the reverberation time. This is something that is kind of subject to whoever is interpreting this. We've seen this be kind of interpreted a couple different ways. whether it's a strict interpretation of it only has to meet the reverberation time, or nope, it's got to meet the entire enhanced classroom acoustics requirements. So just something to be aware of if you're doing renovations, that there is still acoustic criteria that should be addressed.
Yeah. So then besides the code criteria, which would need to be addressed in, again, Florida schools, and it is in the IBC code as well. So depending upon when other states go ahead and adopt that, that may be in other states besides just Florida as well, but Florida requires it now. And there is these other criteria that can be looked at. There's ANSI S1260 is one of the main standards for classroom acoustics. Then we have LEED criteria and WELL criteria as well. If you're going for some of these kind of credentials for your building, they have their own acoustic criteria for classrooms and other spaces. So as we talked about, we have exterior sound source limits. And when we look at this, it's broken up into the 10,000 cubic foot or less, the 10 to 20,000 cubic foot or less, and the greater than 20,000 cubic foot or less, and core learning spaces. So similar to classrooms, just a little bit more kind of broad of a term for them. And it's still that same 35 dBA, 55 dBc for all of these that we're seeing with the code. So we can see that the code aligns very closely with ANSI here as well. So, the other thing we talked about, outside to inside sound levels, the OITC rating. So with that loudest 1 hour outdoor sound level that Keely mentioned needs to be measured to know what that actually is, we can find that and see what ANSI recommends as the OITC for your wall assemblies here, depending upon if there's windows or not within that wall. And even to the point where if your outside sound level for that hour is so loud that it's above 80 dBA, they even say for ANSI, at least, you are not permitted to build a school there. It's just too loud. You're going to have to do too much to that assembly.
This is just a quick case study for an elementary school that we did recently. The site was in Orlando. It was within a GOA noise contour zone, but it was a public school. And so that meant that you had to meet at the time, this was done a little while ago, so the Florida Building Code was not a requirement then, but you had to meet the GOA criteria, which was a 25 dBr sound level reduction and a field test or certification from an acoustic consultant that the sound level reduction was met. And then the OCPS prototype school standard has verbiage in it that requires you to comply with ANSI S12.60 criteria. So looking at this and taking sound level measurements on site, you see, wow, all of these spikes. The LDN, the day-night average sound level, was 63, but we counted there were actually 264 overflights per day. So a very, very significant amount of airplane overflights at fairly high levels. And so, this meant that we needed to look at, all right, what is the 64 dBA? What does that correspond with in terms of the OITC rating for the walls with windows and walls with windows and roofs and walls without windows? So just, kind of the process, a part of a process to go through to help understand what's actually needed when you have a site that could potentially be impacted from something like an airport.
And there's even in some of those spikes for the individual events, we're getting up to 81 dBA. So that average was much lower than that, so that you want to have to watch out for. If you have 264 times a day that you're getting over this 80 dBA level, we want to go ahead and look at possibly addressing that, not just the average. So then again, a little bit more between the ANSI, LEED, and WELL criteria. Again, we mentioned here that background interior sound level. That earlier one we were showing was the exterior. So again, just like the code, it has that same criteria level of 35 dBA, 55 dBc. The LEED and WELL, depending upon the background sound level, That will give you some points for that potentially. Again, you have to meet multiple for these throughout all the spaces, but that 35 dBA is what the lead is asking for, and that's kind of where the kind of most points you're going to see with well. And then the reverberation times, again, we mentioned in the code requirements, it's 0.6 seconds and 0.7 seconds for those kind of first, the less than 10,000 cubic feet and less than between 10 and 20,000 cubic feet. We see these again with lead and with well. Well for that larger section allows a bit of a range of 0.5 to 0.8, but you're kind of looking at this right in there as that 0.6, 0.7 that we're talking about primarily. And again, both lead and well then have additional requirements for the NRC of the material, and sometimes even on different surfaces, not just the ceiling, but the ceiling and the walls in certain percentages. And there's a little bit more for, again, these even larger spaces, especially when you get into things, gymnasiums and natatoriums that are going to be a little bit different too and specialized. ANSI doesn't have those requirements, but you may get them in some of the other. Now, STC ratings, we talked about reducing interior noise as one of these that has to still meet that 35 dBA, 55 dBc from other classrooms. So we're going to look at things like that. And these are good kind of references of, you may not always know how loud it's going to be in that room or what they're exactly going to do. So this is a good starting point of where you can look at for that. Your mechanical rooms and your music rooms are going to need a bit more. So that's why these have these STC 60s when they're going to these kind of core learning spaces, or even to offices in some cases here. Whereas, a standard classroom down here, we have our classroom to another enclosed classroom in STC 50 or so, maybe a little bit higher to a bathroom, a little bit lower to a corridor. And so one of these kind of, to summarize some of the main ideas we were talking about for when you're working within these, especially for shaping and dealing with finishes of the rooms. You want to focus on one, that direct sound. You want to maximize that. And so that's going to be, through the voice, through the diction of the teacher, any amplification methods that may be needed in the larger spaces. You want to maximize those early reflections. So that's going to be those sound reflecting surfaces near the teacher. You don't want them everywhere. They do need to be specially kind of focused on where they need to be. That reverberant tail of, we want to go ahead and try and minimize that. We don't want it completely gone, but we want to go ahead and minimize that reverberant tail and that energy in there. So we're kind of in that right zone of reverberation times. And this is done through the sound absorbent material and the room volume. And again, that background noise, similarly, we want to minimize that, but we don't want to eliminate that. When we eliminate the background noise, then we hear more of the sounds coming in from the other spaces, and other things can be more distracting as well. So we want to have it kind of in the certain range, and right around that, kind of get that 35 dBA is the high end of that, because we don't want it intruding into and making that signal to noise ratio smaller. We want to have that 15 to 20 dB or more signal to noise ratio for our kind of, from our direct sound from our kind of speaker. So, thank you for kind of sitting in there with us for this past, I guess, 50 minutes. I think we're right about on time for there. So we do have some time for some questions. If anyone has them, I think Marilyn from our office has actually been answering them in the chat. If you need to, we have our contact information here. And again, make your buildings sing.
Thank you for your time.
Well, thank you guys. We can give it a few more minutes to see if there's any more questions that come through, but as you mentioned, Marilyn's been answering those.
Well, thank you.
Yeah, no problem. Oh, okay. A question did come through.
So silencers and return ducts are very important, but it's going to depend on how loud that unit itself is going to be the biggest role in it. There are ways if you do have a long enough duct path, or again, things like the acoustical flex duct for the diffusers, line duct. There are other ways that can be impacted, and that can, if it's a quiet enough unit, you may not need one, but there are, again, you do still want to look at that path because it is still a sound path from that mechanical equipment and from that noise that needs to be addressed.
Yeah, silencers are very common.
Yeah.
On both supply and return sides. Just throwing it out there for all you architects who work on education spaces, the new education requirements are a big topic. We have been discussing them at length with a number of our clients as well as school districts, because there is so much that is encompassed with just this little bit of verbiage change. So it's just something that's really important to understand, be aware of, that all new construction education projects need to be incorporating the acoustic design for education spaces that are K through 12, and for many renovations as well. So just something to kind of to keep in mind. And if you would like us to kind of present more in depth to your group, feel free to reach out to us. We have other presentations, and we can go a little bit more in depth on the building code if that's something that would be of interest. Just reach out and let us know.